Welcome to Econ 317. In this instruction video, we will go over the example of another application of derivative, and this is the elasticity of demand. So elasticity of demand, we use notation epsilon, is defined as, using the notion of derivatives, the derivative of Q with respect to P multiplied by P over Q, and apply this formula to different examples of demand. So let's start with a demand. So this is example number 1. Demand itself is given as Q equal to 10 minus 5P. So here we have the derivative of demand with respect to price as the first part which we have to compute. So dq over dp turns out to be derivative of the first term, which is a constant, minus derivative of the second term, which is 5p, and then with respect to p. The first term turns out to be 0 minus the second term, derivative of 5p with respect to p is 5. So the derivative turns out to be 5. Now we can compute the elasticity for any given pair of price and quantity. So let me start with P being equal to 1. If P is 1, then I can see from the demand Q turns out to be 10 minus 5 times 1, 10 minus 5, Q is 5. And now I can apply the formula of the elasticity, the derivative of Q with respect to P, which is minus 5, times P, which is 1, divided by Q, which is 5. And so I have minus 5 over 5, turns out to be minus 1. So this is the example of elasticity where at price equal to 1, the elasticity turns out to be negative 1, or I can say demand is unit elastic at P equal to 1. Okay, I can take one more example of a linear case, but this time I will specify an inverse demand function. Typically, that is what we draw when we draw the demand. So, price is equal to 100 minus 4Q. Remember, elasticity is the derivative of Q with respect to P times P over Q. So, given the inverse demand, I have to now change it to the demand function. So, let me do this. P equal to 100 minus 4Q. I can move the second term on the right hand side, negative 4Q, to the left. So, I'll get 4Q. And I can move the term on the left hand side to the right. So, it will go as negative. So I get 4Q equal to 100 minus P, but I need Q by itself. So I'll divide both sides by 4. So this gives me Q equal to, so now I will write it in full detail, 4Q over 4, 100 over 4 minus P over 4, so that we have Q on the left hand side exactly the way we want it to be. 100 over 4 is 25 minus P over 4. Now we are ready to take the derivative of Q with respect to P, which is the derivative of the constant term 25 minus the derivative of P over 4 turns out to be 0 minus 1/4, so the derivative is minus 1. Now in this example we will pick several pairs of price and quantity to compute the elasticity. This will also show us that the elasticity for this inverse demand as well as the first example depends on the price and quantity which we choose. So let's start with first example of price being equal to 20. So if P is 20, then now I can use the demand function, the one which we obtained by converting the inverse demand into demand, as Q equal to 25 minus P over 4, 25 minus 20 over 4, 20 over 4 is 5, so Q turns out to be 20. So let's compute the elasticity. Elasticity is the derivative of Q with respect to P times P over Q. Okay, so elasticity is minus 1/4, that's the derivative, times P, I chose it to be 20, over Q, it also turned out to be 20. So these two terms cancel out. The elasticity is negative 1/4, or I can say demand is inelastic at P equal to 20. Okay. The second example, now I'll take P to be 60. Again, I can go back to compute the quantity demanded, 25 minus P 60 over 4, 25 minus 15, this turns out to be 10, and so the elasticity, the derivative of Q with respect to P times P over Q, negative 1/4 times P 60 Q 10, this is minus 60 over 40, elasticity turns out to be negative 3 over 2. We can say demand is elastic at P equal to 60. Just to complete another case where we can show that demand could also be unit elastic, I'll take price to be 50. If price is 50, quantity is 25 minus 50 over 4, 25 minus 12.5 turns out to be 12.5. Q is 12.5. I can compute the elasticity. Derivative of Q with respect to P, negative 1/4 times P 25. No, sorry, P 50 divided by 12.5. This turns out to be negative 50 in the numerator. 4 times 12.5 turns out to be 50 minus 50 over 50, that's negative 1, or the demand is unit elastic. At P equal to 50. Okay, so the application of derivative allows us to find out the elasticity even in cases where demand is given as a non-linear function. So we'll give two examples of non-linear demand. The first one I take as the demand function Q equal to P to the power negative 1. Okay, so first find out the derivative of Q with respect to P, which is derivative of P to the power negative 1. We know this will turn out to be negative 1, P to the power negative 2, or minus 1 over P square. Okay, once we have this, now I can write down the elasticity. Derivative of q with respect to p times p over q, negative 1 over p square, that's the derivative, p over q. And now you can see we can have some simplification. P divided by p square is negative 1 over p times q. And if we see the inverse, the demand carefully, remember it is q is equal to p minus 1, which is 1 over p. I multiply both sides by p, I obtain p times q equal to 1. So this can be applied in the formula here, minus 1 over p times q, which turns out to be 1. So elasticity is negative 1. This demand is unit elastic for all price quantity pairs, because I did not assign any specific value of price and quantity. These class of demand functions are called isoelastic demand functions, where elasticity is constant independent of what is the price and quantity pair we choose on the demand function. The last one, I'll take another example just to show we could also have the case where the inverse demand is specified, not the demand. So let's take the example where P is defined as Q to the power minus 2. So remember, I need to take the derivative of Q with respect to P. So I need to transform this inverse demand function into demand function. Let's do that. So I can write P equal to Q to the power negative 2 can be written as Q to the power 2 in the denominator, or I can multiply both sides by q square. So pq square equal to 1. I can divide both sides by p. So I get q square equal to 1 over p. But now I can take the square root. So I have q on the left hand side, 1 over square root of p on the right hand side. I could also write it as p to the power negative half. So this is the demand function if the inverse demand is given as p equal to q to the power negative 2. With this now we are ready to find the derivative. So dq over dp is the derivative of p to the power negative half. This turns out to be minus half times p to the power minus half minus 1. This is minus half p to the power minus 3 over 2. I could also write it as negative 1 over 2 p to the power 3 over 2. With this, I can apply the formula. Elasticity is dq dp p over q, which is minus 1 half p to the power 3 over 2 times p over q. So minus 1 half p to the power 3 over 2, and this is p to the power 1. There is a cancellation going on. We will have p to the power 1 half, and then we have 1 over q. So I could write it as minus 2 p to the power 1 half times q. But if you recall, our our demand function is q to the power q equal to p to the power minus 1 half, which gives me q times p to the power, no, I'll write it q equal to 1 over p to the power 1 half, which gives me, if I multiply both sides by p to the power 1 half, q times p to the power 1 half equal to 1. This is what I will use while computing the elasticity. So minus 1 over 2 p to the power 1 half times q turns out to be minus 1 half times q multiplied by p to the power half is 1. So 2 times 1 turns out to be negative 1 half. So again, I did not take any specific value of price and quantity, which means the elasticity will turn out to be the same regardless of at what point I want to compute. This is again an isoelastic demand, and elasticity is less than greater than negative half, so we will say inelastic, which is inelastic in the given case. And so this is a good point to stop.